Okay, sir, please start the recording then.
Yeah, started.
Okay, so welcome back to lecture 10 on the Riemannian symmetric space. So last lecture we have seen that if you take any element from Hn, U belongs to Hn, then it can be written as U is equal to J plus JW, where this JW belongs to Cn. Okay, and by that you can identify this Hn with this some C2n by this map J plus JW into JW. Yes. 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 Okay. Now similarly, write multiplication by J. By J, this will correspond to some map J tilde from C2 to N to C2 to N, and we have seen this map J tilde Z W is equal to minus W bar Z bar. Okay. So now analogous to the real complex case, then you can identify this MNH with this is the H linear map on Hn is equal to T belongs to M to N C, so that Tj tilde is equal to J tilde T. And what this condition means? This simply means that T respects scalar multiplication Kn by J. So similarly, you can get this thing as GLNH is equal to T belongs to GL2NC, so that Tj tilde is equal to J tilde T. This much we have seen. So now we'll first investigate little bit more about this map J tilde. Okay. Now you take from C2n to C2n, this you take this conjugation map. You take this conjugation map. What does that mean? C of JW, simply it will take Z bar W bar. So therefore this is called conjugation map. And you take this standard complex structure map from C2 to N to C2N. This is by J. And what is J of JW? So J of JW is equal to minus WZ. Okay. So now I look at this.
So C is another map, right? Oh, C is the conjugation.
Yes. Map. Yes, just map. Okay. C is just the conjugation map, and what a J composition C of JW. This is nothing but J of Z bar W bar, and this is really minus of, if you put that, minus of W bar Z bar. So then that will give you, and this is the precise description of J tilde. So this is actually J tilde of ZW. So I am getting this thing that J tilde is equal to J composition C. Similarly, you can show that this is also C composition J. Okay, so now we will understand this thing. What is this meaning of this thing? Tj tilde is equal to J tilde T in terms of this standard complex structure J. Okay. Now, so T J tilde is equal to J tilde T. That is if and only if This is Tj tilde u is equal to J tilde Tu. Okay. Now, where u belongs to where? U belongs to C to n, because J tilde is a map from C to n and T is a map on from C to n to C to n. So then I will replace the T actually T J tilde is equal to this by J composition C. Okay, I will replace that. T J composition C U J composition C T U. Okay. Now this is as a J tilde is J composition C. Now what is C of U? C of U is equal to nothing but U bar. So because I am actually here, previously I was writing this in row form, but you understand that is I always do it in column form. So C of U is equal to U bar. So I write that. So T is a U bar and C of Tu is nothing but Tu bar. Okay, and this T and U are complex matrix. So that means this is T bar U bar. So J T bar U bar. So I am getting this Tj T composition J is equal to J composition T T bar. Okay. Since U bar is arbitrary, I will get T composition J is equal to J composition T bar. So this implies the same thing as this is equivalent to saying the same thing as T bar J is equal to JT. Okay. So this is my thing. Now I will write this MNH in this new form. So MNH is equal to T belongs to M2NC, so that T J tilde is equal to J tilde T. This is same thing as T belongs to M2NC, so that T bar J is equal to J composition T. This T belongs to M2NC, so that Tj is equal to JT bar. And don't confuse with this capital J with small j. Okay, small j is the quaternion element and capital J is the standard complex structure map. Okay, so now similarly I will write this GLNH is equal to T belongs to GL2NC, so that Tj tilde is equal to J tilde T. So T belongs to GL2NC, when C, so that T bar J is equal to J composition T. Tj is equal to Jt bar. Now look at the third equation. This says that GLNH is a closed subgroup of GL2NC, and it says more other things. It is says that it is a matrix Lie group, or GLNH is pseudo-algebraic group. So this says that this from here we see that GLNH is a pseudo-algebraic group. Group and say matrix Lie. Okay, so this is the thing is I have so now you look, we want to see the embedding. Now we have an embedding from this MNH to really where M2NC, and I also write this by embedding Z. Okay. So I want to really look at what is the embedding here. So let U belongs to MNH. So that means U is equal to this A plus JB. This is the quaternionic J. Okay, so here A, B belongs to MNC. And this representation is unique. Okay, unique representation. Okay. Now I want to really determine what is ZU. For that, I have to act on J plus JW. Okay. So that means this is J A plus JB. Okay, sorry. No, sorry. Okay, sorry. ZU is a ZU will act on C2N. Okay. So I just wanted to really find what is ZU. Okay. So for that, I really act on JU on J plus JW. Okay, where JW belongs to Cn. Okay, so that I will write this A plus JB, J plus JW. Now I simply write AJ plus AJW plus JBJ plus JBJW. Now in the previous lecture, I have told you that if this A belongs to MNC, so this is really AJ is equal to AJ is equal to J A bar. Okay, so A bar J is equal to J. So I will use these two things. So how do I do that? So first I will write AJ. AJ I will write this J A bar W plus J BZ, and this BZ I will change that to plus JB bar. Okay, W. So first I write AZ plus J A bar W plus J BZ minus J square is equal to -1, so minus B bar W. Now I will really first couple this thing. So I will write AZ minus B bar W. Okay. So plus J into BZ plus A bar W. So this will actually take this map. What is ZU? ZU will take this map in the column form. ZU will take this ZW to this thing AZ minus B bar W to BZ plus A bar W. Okay. So now I will call this thing that this is A. Okay, so look at this thing A minus B bar B A bar ZW. Okay, so then what is my ZU? So ZU is equal to J A plus JB. This is equal to A minus B bar B A bar. Okay, so now in the row form I will write ZU applied on JW. This is AZ minus B bar W BJ plus A bar W. And I will call this is as let us say first one I will call U. This is U. Second one I will call V. So first one is U. Second one is V. Okay. So this is actually, so I can write this as Az minus b bar w is u, so u plus jb. So I call this is, first one is say 1 and second one is say 2. So look at this 1 and 2. You said that u j plus jw is equal to u plus jb if and only zu applied on jw is equal to ub. I would write that. So u plus j plus jw is equal to u plus jb if and only if zu applied on jw is equal to u. Okay, we will read this notation later. So I just call this as a 3. Okay. 3 is very
Can you just
important.
go back the previous one? So you are calling this to be UV, right? Az minus b bar w,
And this ub is, what is this ub? U is az minus b bar w. B
okay.
is bz plus a bar w. So I am
Okay.
getting this a plus zb, u of z plus w is equal to u plus jb, whatever ub I will get. That will also give me the zu zw is equal to ub.
Okay.
Is it clear?
Yeah.
It is clear? Yes. So this is a very important reason. You will use this thing later. Okay, so from this 3 actually, from 3 you can, this fact, from 3 it is clear. One can check that. You just check that. EU is invertible if and only if ZU is invertible. Okay, so you can check that from 3. Also, there are various ways to check this thing. From 3 it is also clear. So this is the thing you really understand, and then I will give an exercise. So it says let A, comma B, comma C, comma D belongs to MNC, and T is really is A, B, C, D. Then so that T commutes with J, Tj is equal to Jt bar if and only if this is B is equal to what, C is equal to minus B bar and D is equal to A bar if and only if this is something. T is equal to A, B, is equal to Z of A plus J. This is a simple exercise and calculation. So now I
So this basically tells you something about the reverse map, right?
yeah, this says that if Tj is equal to Zt bar, then in M to NC, then it has to be of this form Z of Aj plus Jb. That is also clear from the definition, but just to see this thing in a different way.
No, it's like if you take any matrix in M to N C, who is of this form A, B, C, D, satisfying this, then this will be can be realized as a Z of U for some U in M and H.
Yes, yes, yes. So this is precisely that. Okay, that's statement. So now I want to really, so So we have this map from MNH to really M to MC. This is the map Z. So, and what is Z? Z of A plus JB is equal to A minus B, AB plus minus B bar A bar. AB belongs to what? MNC. Now, so I just wanted to write these properties of Z. So similar to the first place, you will get a Z of U1 plus U2. Z of U1 plus Z of U2. U1, U2 belongs to MNH. So second thing is Z of alpha U, alpha of ZU, alpha belongs to R, U belongs to MNX. Third thing is Z of U1, U2, Z of U1, Z of U2. First two things are very clear because complex means the way it will add matrices. This first two things is very clear. Third thing is also clear if you think little bit. Okay, so I leave it an exercise. So what my suggestion is first you try to do it by inspection, then you do it by calculation. Actually, it will increase some familiarity with MNH. Okay. So exercise. Fourth thing is Z of U star. This property is also important. Z of U star. Okay, fourth property I will do. Okay. So 2 pop 4. So let U is equal to say A plus JB. Okay, A comma B belongs to MNC. Okay, let us write A comma B belongs to MNC. Okay. So what will be U star? This U star is equal to U star is equal to this is A star plus JB star. This is the quaternion JB star. Okay. Now you use this fact that JB star is equal to B star J star. Okay. And J star is equal to minus J, right? So this will be minus B star J. So you get A star minus B star J. Now I have B star is a complex matrix. So I have that property that so this will be A star minus J B star bar. Okay. So that will give you the A star minus J B transpose. Okay. So what will be ZU star? ZU star is equal to A star minus B transpose. Okay, this is first in the first column you write AB. What was the A and B, then you take minus B bar A bar. So A star minus B transpose, and so I'll take a minus of that thing. So B transpose bar, and this is really A star bar. So this is B by definition. This would be A star B star minus B transpose, really A transpose. Okay. Now this is my thing. ZU star. Now what is ZU? ZU is equal to AB minus B bar A bar. Now what is ZU star? First I will take the transpose, then I will take the bar. So first if you take the transpose, then A transpose minus B bar transpose, B transpose, A bar transpose. Okay, only transpose I have taken. So I have to take this bar everywhere. So if I will take this bar, first one will be A star, second thing is B star, and bar will cancel out, minus B transpose, the B transpose, A transpose. Okay. So this is nothing but ZU star. Look at this two things, this thing and this thing, these are same. So ZU star is equal to ZU star. Okay. So this is the proper proof of 4. This will be these 4 properties are very important properties of this thing. Now I recall in the previous lecture I have seen that the notion of determinant, usual notion of determinant, is not useful because it doesn't satisfy various properties and many properties which we want. So now you want to define a new notion of determinant, and this new notion is something like this. Definition: let A belongs to MNH. We define the determinant of A by this thing, determinant of ZA. Okay. I really take the embedding inside the complex matrices from quaternion picture in the complex matrices, and I look at this determinant of ZA. By definition, this is a complex number. Okay. So this will be the definition of determinant for us. Okay. So let us write this new notion of determinant. So since this is what Z of U1 U2 is equal to Z of U1 into Z of U2, because of this property we'll get that we will get that determinant of AB is equal to determinant of A into determinant of B. Okay, so A comma B belongs to minus. Now the thing is we will get this. Okay, similarly as ZU star is equal to ZU star, you will get that will get determinant of U star is equal to determinant of U bar. Okay, so this is the thing we will get, and similarly by determinant, if I am talking about determinant from of some quaternionic matrices, then you must understand that this is the notion of determinant. So analogously I can we define this trace of A, okay, is equal to this trace of ZA. Okay. So A belongs to C MNH. This notion of trace we do not need much, but this and trace of AB in this thing we will get trace of AB is equal to trace of B. You can check that. Okay. So now okay, so you have seen that just use a pair space. So let okay, U belongs to MNH is invertible. This implies really ZU is invertible. Okay. Now, if ZU is invertible, that means this is if and only if determinant of ZU is equal to not 0. This is simply if and only if this determinant of U is non-zero. What is the determinant of? Because determinant of U is defined since determinant of U is equal to determinant of Z by this new definition of this. Now you can say that this now you can say that this GLNH, this is really A belongs to MNH, so that determinant of determinant of A is not equal to 0. Now this you can say that. Okay. Now I really okay. So let us understand this thing. So okay. So this okay. Now MNH. We know that this MNH is equal to really. This is T belongs to M2 and C, so that Tj is equal to Jt bar. Okay. So, and I have told you in the last class, this is quite not correct, because left hand side a map from Hn is a set of left hand side is a set of maps from Hn to Hn, and right hand side is a map from C2n to C2n. Okay, but there is an identification you are using, and for that reason I am really writing this is equality. For this moment, to be very precise, one should write like this: Z of MNH is equal to this thing, if you are very precise. Okay, and for a moment that you really we will write that Z of similar. Okay, for a moment I will write that Z here everywhere. So Z of GL and S is equal to, say this is P belongs to GL2 and C. Okay, so that Tj is equal to Jt bar. Okay. Now, what is the Lie algebra of Z GL and S? Lie algebra of Z GL and S is something like X belongs to, if you will calculate this thing, M2 and C, so that Xj is equal to Jx bar. Okay. So you can look at this as an exercise. Now the thing is, what is this? This is nothing but, this is, if you look at this definition, this is equal to Z of MNH. So now, and this is a subalgebra of M2 and C. Z of MNH is a Lie subalgebra of M2 and C. Okay, we know the Lie algebra structure there. Okay, so what I am getting, I am taking something like GLNH. This is my quaternion picture, and via this map I am transferring to this complex picture. I am taking an embedding inside this GL2 and C, and this is ZGLNH. Okay, so I am really and if you look at this Lie algebra of ZGLNH, this is Z of MNH. Okay, so this is Lie algebra of Z of GLNH. I am I am in the now in the complex picture. Now I want to go back to the quaternionic picture. Okay, and actually, you know that I have seen that this MNH is a real Lie algebra in the quaternion. Okay, so I conclude from there that MNH is the Lie algebra of GLNH. That is the question. Okay, so I am saying this once more. I start with the group GLNH. This was in the quaternionic setup. Then I take this map Z, then I go to the complex setup. Then I get that Lie algebra. This is still I am in the complex thing. Now can I go back to the quaternion thing and conclude that MNH is the Lie algebra of GLNH. Now I can conclude that because if you look at this map Z and if you verify this property 1, 2, 3, this property 1, 2, and 3, this map Z will be a Lie algebra isomer. So this is a very important thing. So using 1, 2, and 3, we see that properties of Z 2 and 3. Z, we see that Z from MNH to ZMNH is a Lie algebra homomorphism. Is a Lie algebra isomorphism. Sorry, not Lie algebra isomorphism. And for that, for this reason, you can say that Lie algebra of this GLNH is MNH. Okay. So I can GLNH, small GLNH is your MNH. Okay. Mithunda, is it clear?
Yes, Muna.
Okay. So the thing is, actually mostly people actually go to this complex setup and do whatever they and like to stay in that complex setup. But I am very flexible in that thing. Whichever is convenient for me, I will use this thing. And I will really, and another thing, I will, since you know that this jade is just a identification map, so most of the time I will not write Z, or depending upon the situation I may write Z, but you have to keep this thing in your mind that there is some identification is going on. Okay, so this is the
Muna, I
thing.
just have a question. It may be
Yes,
obvious also. So this MNH, the map taking MNH inside this M2 and C, that map is not
yes,
onto, right?
not onto.
So I'm just trying to understand how small is how small this Z of MNH compared to M2 and C. So if you see
As
them, like, is it
in the sense of measure, you are saying that
not measured? So both are vector spaces, right? As the
but
dimension
okay,
same.
dimension will be not be same because
Also, you can see it
okay,
as a
I will
Lie
ask.
algebra, right? You can say
Yes,
them
the
as Lie
dimension will
groups,
not be
and
never be same. The
because
dimension will be never.
you can see them as Lie groups, Lie algebra, right?
Yeah, embedding MNH.
Or
Yeah,
you
least
take
of the algebra.
GLNH, take it inside GL2 and C.
It is a least subgroup.
It's a Lie subgroup, but it's smaller than that, right?
It is definitely will be smaller than that.
Because what is the real dimension of GLNH? Let's say it's a manifold. So what
GLNH.
is the dimension of the manifold?
This will be. It is obvious because Lie algebra of GLNH is MNH, right?
Yeah.
So MNH has n square quaternionic coordinates, right?
Uh,
Therefore,
n square times 4.
each n square, 4n square. Its
4n square.
dimension is 4n square.
And what about M2NC? It is 2n times. What is dimension of
M2NC.
it? Yes. That is again 4n square, right?
M2NC. Just wait. This is actually
A mistake probably.
2n into 2n.
Hmm.
This is 4n square complex coordinates, right? Into
Okay.
2,
So it's
8n
double
square.
basically.
This
8n
is the
square.
double.
Double. Okay. Okay, I got it. Yeah. Thank you.
So this is the system. Now I define a new group. This is so SL and H. This is really, this is same thing as A belongs to M and H. So the determinant of A is equal to 1. Determinant is the new notion of determinant. Now it is clear that this SL and H is a group. Clear that SL and H is a group. So now SL and H is equal to A belongs to M and H. Determinant of A is equal to 1. So what I will do, I will the same thing as this A belongs to GL and H. Okay, so that determinant of A is equal to 1. Now I can write this thing that in the complex setup, so suppose, so in the complex setup I can write that A belongs to GL2 and C. So the determinant of A is equal to 1 and AJ is equal to J bar. This condition will be there, and from so I will make two observations. This is so these two conditions, A belongs to GL2 and C, and AZ J bar, that means A belongs to GL and H. So this is same thing as SL and H is equal to GL and H, okay, intersection SL2 and C. Okay, these two conditions, AJ is equal to J bar, A belongs to GL2 and C, that means that belongs to GL and H, and determinant of A is equal to 1, that means SL2 and C. Okay, so this actually I should write here Z of GL and H, but I told you that I will not write that thing. And another thing is this you can write that this condition is like that A belongs to SL2 and C. So this AJ is equal to J bar. You can also write. Okay. So let us okay. So this is what I am getting. So I will get this SL and H first. GL and H intersection SL2 and C. This is important. This is going to important, and this is also going to SL and H is equal to A belongs to SL2 and C. So that AJ is equal to J bar. Okay, this is going to now from this thing it is clear that SL and H is just pseudo algebraic group. Clearly SL and H is a pseudo algebraic group. So this is clear. Now I will go to something defined called quaternionic inner product. So let P be a H. Okay, so let us see. Let U comma V belongs to Hn. So U is equal to say U1, U2, Un, and So ui belongs to H. Okay, UM, right? Better. V is equal to say V1, V2, Vn must H. So I define this thing U inner product P Hn. This is the called standard quaternionic inner product. This is really M is equal to 1 to N Um bar Vm, and this is called standard quaternionic inner product. Okay. So now let us see some properties. First property is very clear. This if you will add u1 plus u2v, I should not really use write this u1 plus u2. I should write u plus w. Okay, w is a quaternionic element. Do you w belongs to Hn? Okay, u plus wv is uv plus w. You put here Hn. Okay. So second property is u. This v1 u v plus w. This is uv uw. Just do it just by mentally. Okay. I will give you some time. Okay. The third property is something like I suppose I will multiply q in this thing. Right, multiply q, and what I will get. So suppose I will multiply this q here. Okay. Then um q bar will be there. Okay. So what is q bar? This is really q bar is equal to q bar bar. Okay. So q bar will come to the first. Okay. So that's for that reason I will get here q bar uv. Okay. Fourth property is u vq. Okay. So if you q will be multiplied from the right, it will q will be multiplied from right to v, then components will be vmq. Okay, so q will be in the right hand side, so this is uvq. Okay, now fourth property is really is also important. Ub bar is equal to vu. Okay, you use this property that ab bar is equal to b bar a bar. Ab belongs to H. Okay, so fifth property is clear. So sixth property is this property will get that uu greater than 0 for 0 not equal to u belongs to H. This is the positive definition. This will let us keep this thing for a moment so that you can see it. Okay, so now definition. So let V be a H vector space. A map, this I call this thing from V cross V to H. It's called an first H inner product. This is quaternionic inner product. H inner product So if it satisfies properties from 1 to 5. 1 to 5 mentioned above. Okay. 1 to 6, sorry. 1 to 6. 1 to 6. Now if it satisfies first 5 property, then it will be called an H Hermitian form. So this be H Hermitian form if it satisfies properties from 1 to 5. Okay. So if you satisfy 5 properties, then it is called H Hermitian form. Or and sixth thing is just positive definiteness. You are adding to H Hermitian form. Okay. Now I define this SPN, symplectic group. Okay, so you take this. Okay, you take this HN, and this be the standard H inner products. Okay. Let U1, U2, En be the standard orthonormal basis. Basis of Hn. Okay. Now you can write that En and Ek, this inner product on Hn. This you will get that delta Mk. By definition, you can check it. So now the thing is, you take let U belongs to Hn. Now what is UU? Okay, I have not defined the norm of this. Okay, so I define this. Okay, okay, you define this norm of UHN is defined by this thing. This is UU Chen. So analogously, you can define this for we define norm for H vector space. Okay, so H inner product space, not vectors.
Mona, can you go back to the previous page?
Yes. Yes.
So just above what you started this inner product. So this inner product is a function from Hn cross Hn to
H.
H, right?
Yes.
And now you go to the next page. So then what do you mean by taking this root?
Actually, you know that there is a positive definite condition 6 number. Look at the
Yes.
6th thing. So that
Okay.
means you got an answer one that is
Oh,
real
it's always a real
positive.
number. Okay.
Yes, yes.
Sorry.
Okay, that's okay. So don't have to say sorry. So this is the thing. Analogously, we define a norm for H inner product space. So okay. Now you define what is this thing. So norm of UHN square. So this is really m is equal to 1 to n, um bar um. So that is same thing as m is equal to 1 to n um norm square, and this is really R4 norm square. Okay, I have in the past lecture, in the previous lecture we have seen. So if you look at this thing, this is really if you take u identify if you identify u with of Hn with R to the power 4n, then this is actually u norm of u R4n square. Okay, so this is really say that norm of UHN. Okay, this is really say that norm of UHN is equal to norm of U R 4n. Okay, so now I define this group SPN. Okay, so SPN is equal to really yeah. So this is really A belongs to MNH, so that A U A B. This is the standard quaternary unit part. U B H N for all U comma B not H N. So this is my thing. Now you will get that SP. Sorry. This SPN is equal to A belongs to MNH, so that A of EM EK. This is actually EM EK. So 1 less than equal to M less K less than equal to N. But this EM EK inner product is delta MK. So I write that this is equal to delta MK. Okay. Now, if you are really want to write purely in matrix form, this is you will get this A belongs to M and S. Really, it into A star A. This is equal to identity. Okay. So now this is a group. Actually, you can check that, and this is equivalent to saying that A belongs to GL and H. So that A star A is equal to identity. Yeah, I have told that this in MNH actually you always equip with this topology from R4n square. Okay, always you are equipping the substrate topology from this Rn, some Rn or some n. Okay, so now from this thing. Okay, so I have shown that GLNH is a closed subgroup of GL2NC. Okay. Since GLNH is a closed subgroup of GL2NC, and there is one more condition that this implies SPN. SPN is a really is a closed subgroup of GL2NC, so this is matrix Lie. In fact, it is a pseudo algebraic group. This implies SPN is a matrix Lie group. So in fact, it is a pseudo algebraic. So now let say that A is equal to say U1, U2, UN. This belongs to say MNH. Okay. So A belongs to SPN. What does that mean? A belongs to SPN if and only if this A of EI, EM, A of EK, this is equal to delta MK. So 1 less than equal to MK less than equal to N. And AEM is nothing but UM, inner product UK. This is equal to delta MK. Okay, so A belongs to APN, and this means A belongs to APN if and only columns of A forms an H orthonormal basis, basis for HN. Okay, this is clear. Now, okay. So let sorry, let A is equal to say U1, U2, or UN. This belongs to SPN. So I told you that this norm was this implies this norm on HN. This is 1, and this is same thing as, that means norm as R to the power 4n norm is equal to 1. So that means SPN is a bounded set. Is a bounded subset of MNH. So this was a closed subset of MNH, and this is bounded subset of MNH. So this implies, okay, SPN is a compact subgroup of GLNS. Closed and bounded, this is compact. So now this is the thing. Now I really okay. So now prove okay. So proposition. This is so let V be a H inner product space. So and let W belongs to V with norm of W is equal to 1. This is the inner product norm. Then there exists an orthonormal basis. This is W1, W2, Wn of P with W1 is equal to W. This is a very Euclidean type result. So proof is very simple. So let W is equal to, this is span of Q, H span of V. This vector V span of. So now let W power is what? This is W belongs to V.
What is V?
Oh, W. Sorry, I it should be W. This will V belongs to V, so that VW is equal to inner product of TW0. Like this, the Euclidean case you define. So we will use this by proof is by induction. So check that.
You're basically doing the Gumsmith process, right?
Yeah. Okay. So
I think that involves only ring structure, field structure. Commutativity
okay.
probably is not required, so that should be possible.
In this case, okay. So this is not exactly Gumsmith. I will write that. In this case, E is equal to W plus W power, and dimension of W power is equal to dimension of W dimension of V minus 1. Is by induction on, actually I don't on dimension of V. So this is a simple thing. By I'm just writing this for completed by induction hypothesis. There exists an orthonormal basis W2, W3, Wn of W power, and we set W1 is equal to W. Check that W1, W3 and Wn is the required orthonormal basis. So this is the thing. Just I can really extend this W to a basis. That's all. Orthonormal basis. Okay, exercise. Let G be an H inner product space. Space. Verify that graph orthogonalization process is possible in B. Okay, so this is thing. Now next proposition is position this SPN acts transitively and acts continuously transitively on this thing Hn1. This B belongs to Hn and this is norm of B is equal to 1. And this action, since this is a matrix multiplication, this action is continuous. Okay, this I don't want to really write. Action is continuous, and it is also smooth actually. In fact, the smart action is actually smooth if you equip the smooth structure, Lie group structure. Action is smooth. Okay, so and this B is Hn is equal to 1. That B is a quaternionic element, so it has really n quaternionic coordinates. So this is really actually homeomorphic to S for n minus 1. Okay. So proof is I will use that previous proposition. Let W belongs to Hn1. Okay. By previous proposition, there exists an orthonormal basis W1, W2, Wn with W1 is equal to orthonormal basis of Hn with W1 is equal to W. Let A be the matrix. This is U1, W1, W2, Wn, and A of U1 is equal to your W1. This is really equal to W. So I can so every element, if you look at the action, that a free all element of Hn1 is in the orbit of U1. So that, and since this is really A is
Kunal,
columns
can you just repeat? So you want to show the action is transitive. So you are picking. So how are you starting?
so W belongs to Hn1. Okay.
W belongs to Hn1. Okay.
By
And then
previous
what are you going to?
proposition, by
Yeah, you
previous
can
proposition, I am
completed your
using
basis.
this. Okay. So there exists this is I am taking this matrix A is equal to W1, W2, Wn. I am putting those things in columns. Okay.
Okay.
Now since columns forms an orthonormal basis of Hn, though this belongs to SPN. Because I have shown that I have told you that something belongs to SPN, this belongs to that means this is equivalent to saying that columns of A forms an orthonormal basis. So for A U1 is equal to W. Therefore, this action is SPN acts transitively on this Hn1. Okay, and this is homeomorphic to S4n minus 1. Now, okay, some fact. This is so let G be a topological group, and I will take 5 more minutes. Okay, let A be a subgroup of G, so that AF and G by F are connected. This then G is connected. So this is really proof. As exercise, I will. This is a standard fact in the thing that let G be a topological group and A be a subgroup of G, so that F and G by F are connected. Then G is connected. I will prove now the SPN is connected. Proposition this. This SPN is connected. Proof I will do it by induction. By induction on N. So first I will look at this SP1. SP1 is really Q belongs to H. Norm of Q is equal to 1. This is my definition of 1 H is equal to 1. So that is really equal to S3. Hence SP1 is connected. Now that implies that assume that SPN minus 1 is connected.
So you proved that that action is transitive, right?
And that action is smooth also, continuous.
That action is smooth, but is that that action does not have any fixed point, right? That also means the action is 1 1 also, right?
You mean faithful?
Yes, because I am. I think you are using the fact that you are identifying HN1 with SPN or not.
No, I am not identifying it. I am
Okay,
just.
you are proceeding by
I
that
will.
action.
Yeah.
So for one
assume
case
that
it is for one case it is actually equal, right? SP1 is equal to H of 1,
yeah.
right? For one case it is equal,
Yes,
right?
yes. Yes. So hence SPN is connected. Assume that induction hypothesis SPN minus 1 is connected for n greater than equal to 2. Okay. And I want to show that SPN is connected. Let G is equal to SPN. Okay. And I look at this F is equal to stabilizer of what? U1 inside G. Okay. So let T belongs to F. So that means T is equal to some U1, U2, UN. Okay. Now T of U1 is equal to U1. This will imply that U1 is equal to this is U1. Okay, so now as F is a subset of SPN, this will imply that UI, UM, UK is this is delta MK. So T is of the form this is something like 1 0 0 0, and there is something here. Okay. Now I will. So if you use this two condition, MK is equal to delta MK, this star and double star, you will show that using star and double star, one can see that this is F is equal to 1 0 0 A, where F A is equal to A belongs to Spn minus 1. And this is homeomorphic to Spn minus 1. Okay. Now what I am getting, the stabilizer F is homeomorphic to Spn minus 1. So this is really and by standard theory that G by F is really homeomorphic to Hn1, and this is S4n1 minus 1. This is by general theory that
What do you mean by standard theory?
means okay. So what I'm saying that so suppose G acts continuously on. Okay, let me write in here somewhere here. Okay, let us see. So act.
5 minutes.
So let G acts on
2
X
minutes बाद.
continuously, and let O belongs to X continuously and transitively. O belongs to X, and this F is equal to really stabilizer G O, then G by F is homeomorphic to X. This is a homeomorphism. Okay, so if you are very pedantic, then you have to assume this weird, and this is condition that G is really your what is G is actually sigma compact, or G has countable base. You can G is locally compact.
See here, G is compact, right? So there's no problem.
Has countable base. So this is a precise statement. If that G acts
No,
on
but
X continuous.
how are you getting that G mod F is equal to H1?
G mod F is equal to Hn1 because
Yes.
G acts on X. G acts on Hn1 transitively. This since okay, let us write here. Since G acts on Hn1 transitively.
Yeah, fine.
Okay. Now F is connected by induction hypothesis. So SPNR is this is connected by induction hypothesis. And G by since S4n1 is connected, this implies okay, G by F is connected. Now as F and G by F is connected, we see that G is equal to SPN is connected. So in the and this finishes the proof. And I have told you that in the manifold setup, this is connectedness and path connected are equivalent. So that is the thing. Now I want to give you one exercise using the idea of previous proposition. So that UN, SUN and SUN are connected. Okay, so this is the thing, and I would like to stop it here. So, and another thing is actually uh, this is the thing, and we will need at most 2 classes to finish this classical Lie group thing, and then we will move to Riemannian symmetric space. So, for that reason, that you need to really, it is not possible to define all those notions, basic notion for Riemannian geometry and Lie group theory, and I just want to all of you, to those who do not know, just to look at this definition like Riemannian manifold, uh, some definition like Riemannian manifold connection and submanifold, this embedded submanifold. These some basic definitions actually. I need that parallel transport so that you will be convenient. You will be very comfortable on this thing. We'll need at most 2 lectures to finish this thing of this classical Lie group. So you will consider next class this SP P comma Q, SP power up 2n R, and SP2nC probably. So let us see. So I would like to stop. If there is, are there any question? I would be happy to answer.
Thank you.
Okay. Any question?
So we'll stop recording. Puna.
Okay, sir. Yes, sir.